1,1,1 trifluoro 2-methyl ethane. You can see this 1,1,1 trifluoro 2. That's position. If you call this position 1, that would be 2-methoxyethane, and then you add chlorine. And once you do that, once you add chlorine, all that is happening is that two of the methyl groups on the terminal two of the hydrogen on the methyl on the terminal methyl group will be replaced, and therefore we'll have trichloromethoxy. This will be now trichloromethoxy. Remember, the name normally used is for the much longer compound. So now you can call these. There are different ways of naming. So sometimes you find different names. So it can be 2-dichromethylmethoxy, 1,1,1 trifluoroethane, and then you put hydrogen fluoride and antimony chloride plus hydrogen fluoride, and it now gives you the 2 at position number 2, position 1, 2. So it's 2-difluoromethoxy. Then difluoromethoxy, 1,1,1 trifluoroethane. Then, of course, it's ethane. Remember, we name the name from the longer chain. The basic name is from the longer chain, and therefore this we are using it as a substituent. Then again, you add chlorine, and once you add another chlorine, you get our isoflurane. Do remember we did mention isoflurane is a positional isomer of N-fluorine, where the chloro group is in isoflurane, it is in position 2, and in N-fluorine, it is in position number 1. Important for us to look at we had looked at the metabolism. I think I also added something about the metabolism of isoflurane. I can get it somewhere, of N-fluorine. So again, do remember, we did mention when we were looking at the metabolism of paracetamol, because we did paracetamol with you. Remember this enzyme. The enzyme cytochrome 2E1. Of course, it's a cytochrome P450 enzyme, but it's usually very notorious in actually resulting in highly toxic metabolites. Remember, even when we looked at it when we were looking at the metabolism of paracetamol. So that is our N-fluorine. Again, we have said N-fluorine. As you can clearly see, it's a constitutional isomer of isoflurane, and it can be metabolized by cytochrome 2E1, a mixed function. And if that does happen, then you will have here, you can see this fluorine, chlorine. Here, of course, there is a hydrogen. Remember, here there is a hydrogen, and there will be oxidation of that hydrogen to give us the alcohol. So that is the alcohol product. And once you have that, then you can lose your hydrochloric acid. And once you lose your hydrochloric acid, you can see our compound. Our compound is whereby those two fluoro groups and oxygen there. You can see this chloro group and this double bond here. Again, we will get the names of these compounds. You can be able to get the names of these compounds. So because of this chloro group, and also because of this oxygen here, this oxygen is highly electron withdrawing, chlorine is highly electron withdrawing. So even if this does not give us the acetic acid, because it can, even if it doesn't give us the acetic acid, this compound as it is has very high, the chlorine highly electronegative, the oxygen highly electronegative. This carbon here, let me get my marker again. This carbon here, this carbon there has a delta positive, and that carbon, because of course it has also a delta positive, it can also bind. It can bind with proteins. That carbon can bind because it's highly electrophilic, and that's what happens. Remember, proteins are nucleophilic. The proteins will have an amino group, and that amino group now can come and bind here with replacement of the chlorine. So because this carbon here is highly electrophilic, it has a positive charge because of the pull. The chloride ion can leave very easily as a chloride ion and replaced by the protein. And once you form the drug protein adduct, toxicity. That is what can bring us hepatotoxicity or renal toxicity. So that is how some of these drugs, and we had mentioned earlier, that when you get an electrophilic carbon created within a metabolite, there is a very high likelihood of toxicity or organ toxicity. So that's how enfluorine, we had also done for halothane. Remember, we did say halothane can form the trifluoroacetic acid, and in forming the difluoroacetic acid, again, that acetic acid has an electrophilic center, and that electrophilic center will be responsible for toxicity. I think this we had already discussed. The only one I want us to, even this we had discussed. This we had already discussed, if I'm not wrong. Yes, we had discussed this presence of double bond increasing chemical slide. If we hadn't, we can always go back just to remind ourselves. This is about the SAR for inhaled anesthetics, can be summarized as follows: halogenation of the hydrocarbons and ethers increases the anesthetic property. I think we had halogenations of the hydrocarbons that induce arrhythmias in the following order: fluorine less than chlorine, less than bromine, and less by iodine. And that explains why we are using quite a lot of fluorine. And of course, mainly used only in halothane itself. So we are preferring fluorine and chlorine because they have lesser ability to induce arrhythmias. Due to the presence of asymmetric halogenated carbons in ether, they are better anesthetics. Halogenated methyl ethers are more stable, more potent, and have better clinical profiles than halogenated diethyl ethers. That is just has been found out on clinical trials. Fluorination increases the stability and decreases the permeability. We had already mentioned that. Complete halogenations of the alkane or ether decreases the anesthetic potency and increases conversant property. Remember, we did mention for these drugs, if you could have either of the terminal carbons with a hydrogen not fully halogenated, with the exception, of course, with when carbon is one, that is for methane, then you get better activity. Presence of double bond increases chemical reactivity and toxicity. And indeed, in most of these compounds, we do not have double bonds. I mentioned this only. I wanted us also to look at this. This is showing us the metabolism of the various compounds. Metabolism of the various compounds. You can see we are starting, that is enfluorine. And as we have said, it is acted on by the cytochrome 2E1. It can be acted on by the cytochrome 2E1, and in so doing, you can see the resultant compound. So we have that CF hydrogen. So the other one, oxidation of that one. So this one, they are doing it a little bit differently, but anyway, it has a hydrogen here, and it has a hydrogen there. So oxidation can come at any point. So in this one, they have started oxidation at this particular point, but the product is almost the same. Oxidation at that point with loss of the chloro group. So oxidation at that point with loss of the chloro group to give us this compound here. And that again is a compound we are saying has very high electron, and it's a very potent electrophile. And because it's a very potent electrophile, then it can covalently bind to the proteins, of course, the proteins through the amino group. It can covalently bind to the proteins with formation, with replacement of the fluoride. And of course, if this fluoride is replaced, remember we did talk about the fluoride itself also has its own toxicity, although these compounds do not form very high concentrations. So this can be of what we are calling protein adduct. And if you have that adduct, it means, again, there will be hepatotoxicity, there can be renal toxicity, and there can be generation of fluoride, which can also cause toxicity. Alternatively, of course, we have said also this compound can react with water. It can react with water, again, with loss of the fluorine to give us the acid. And even the acid, of course, it will cause us also toxicity. Here is has to have very high, it's a strong electrophile, can give us, there can be covalent bonding with the proteins. All, of course, acids themselves do have their own toxicity in bringing about metabolic acidosis. All this compound now, once it is formed, it can undergo glucuronide conjugation and it will be removed. Once it undergoes glucuronide conjugation, it will be removed in the urine. So then you have, of course, isoflurane. This, I think, is the one we had discussed. Isoflurane again, and you can see that is a structure very slightly different from that. And again, it can undergo oxidation using cytochrome 2E. And if that happens, again, it's this oxidation of that hydrogen there, oxidation of that with the loss of the fluorine to give us, again, once you lose the fluorine, remember, we mentioned the fluoride has toxicity, to give us this compound, which is a chlorocarbonyl compound, again, a very strong electrophile, considering that also these fluorines are pulling away electrons. So this is a trifluorochloroacetic acid. So you can see that this is pulling away. This is pulling away. These fluorines are pulling electrons from the carbon. The carbon is pulling also electrons from that. That oxygen is pulling away electrons. The chlorine is pulling away electrons. And if that happens, then of course, this carbon will be delta positive and therefore can also bring about adduct properties or adduct compounds. But at the same time, this compound can also react with water, as we have seen, of enflurane to give us now the trifluoroacetic acid. The trifluoroacetic acid, again, giving us metabolic acidosis, and of course also giving us metabolic acidosis and a very strong electrophile, which again can bring about covalent binding to macromolecules and hence toxicity. It can also, of course, undergo, it can bring an acid. It can also be excreted the way it is, or it can undergo conjugation and it's removed from the body. Desflurane is also another of the ether, halogenated ether. Structure CF2, oxygen, CF there. So it has 1, 2, 3, 4, 5, 6. So they are almost the same with rearrangement of these fluorines, or with one or so difference in the number of fluorines. Again, it can undergo through cytochrome P456, cytochrome 2E, again undergo oxidation of this. It would always undergo oxidation, where normally it would go oxidation where there is a hydrogen, so there is high fluorine. It's like it has undergone some sort of a rearrangement, because this is F, hydrogen, that is that one, then oxygen. So this now has become HF. So there's a slight rearrangement, and this now is F1. We've lost F, oxidation with loss of one fluorine. So there is oxidation with loss of one fluorine. So oxidation of this group there and oxidation of the group there, again giving us a very strong electrophile, and it's giving us that very strong electrophile. Then again, it will do the same thing as we have talked about. Again, this compound can undergo react with water. Remember, water is a very strong nucleophile, and that is why it is reacting with this compound. So it can react with that compound again to give us, all of them are giving us the difluoroacetic acid, again, cause of course also still covalent binding with the macromolecules and urinary excretion. Of course, in some of them there is also some spontaneous cleavage. There's some change, or there's some change of the arrangement of the atoms, but finally we are seeing in all of them, in almost all of them apart from the first one, we are getting these two, and of course in halothane we are getting the difluoroacetic acid, and the difluoroacetic acid, as we had said, is very, very toxic, and indeed can bring about a lot of hepatotoxicity. So neither enflurane nor isoflurane undergoes reductive metabolism. You have seen they undergo oxidative metabolism. In common with halothane, both drugs are metabolized by hepatic cytochrome 2E1 via dehalogenation, as we have seen. So there is oxidation followed by dehalogenation. The metabolites are reactive intermediates. Let me remove this. The metabolites are reactive intermediates that bind covalently to proteins, and I've explained why it is, because that carbon has a delta positive, and therefore we bind the nucleophiles that are found in proteins, including sulfhydryl groups, like if you have cysteine, or amino groups. And you know most proteins have amino acids. In humans, the extent of metabolism of N-fluorine is up to 4%, and of isoflurane is much, much lower, 0.2%. Have lesser toxicity than N-fluorine, and therefore it is even more popular than N-fluorine, which is markedly lower than the extent of halothane metabolism. Remember, halothane, I think we said it was up to 20%. So therefore, you find isoflurane is safer, because once it gets metabolized, it gives us, of course, there is loss of the fluoride, or formation of the fluoride ions, there's formation of the reactive metabolite, and therefore you want the one which has a very low degree of cause good activity. Metabolism of N-fluorine proceeds by reactive metabolite, of course, even the others that either react with water to form an acid that is excreted in urine as a glucuronide conjugate, or binds covalently to the liver proteins to form protein adducts. That indeed is not only for N-fluorine, it's basically for the three of them. Cytochrome 2E1 mediated oxidation of isoflurane is the other one, proceeds again via reactive intermediate that are believed to include trifluoroacetylfluoride. So we have looked at that. There is excretion of inorganic fluoride and trifluoroacetic acid. There is also covalent modification of liver proteins, resulting in the formation of trifluoroacetylated proteins. So these are the results. So once, like even isoflurane undergoes metabolism, you can have excretion of fluoride ions and trifluoroacetic acid. The trifluoroacetic acid is also toxic, and of course, there can be acetylation of the proteins, or formation of protein adducts, and that can result. So that I had not decided. I thought it's important that I go back so that we look at the metabolism of those volatile halogenated ether volatile anesthetics, and be able to account for their toxicity. I think all these other ones we had done. That is the only bit I thought I should go back to. And I think with that, we had gone actually up to methotrexate and even the pentosodium, and we discussed the SAR of the barbiturates remains even for these drugs. For them to be able to cross the BBB, they must obey the basic structural, they must have the basic structural features required for these drugs to cross the BBB. But for these two drugs, methotrexate and thiopentosodium, then they enter another category whereby they have their carbon content at position number 5 is very large, which gives them very high lipid. For methotrexate, of course, there is also addition of a methyl group at position number 3. This gives these drugs very high lipid solubility, and because of the very high lipid solubility, they will pass, or they will be distributed into the brain rapidly. They will have a rapid onset of activity, and that is really what we want for a general anesthetic. But they will have also a short duration of action, not very good for maintenance, as we said last time. You need to give the halogenated ethers, or you give them as an infusion of continuously to maintain the dosage, because we did mention, because of deputization, they will have a short duration of action. I think with that, we are done with the general anesthetics, and then now we want to look at the centrally acting muscle relaxants. Again, these are very short topics, very, very short, not very, I really try to look for details, but we are very scanty. So we look at the central acting muscle relaxants. Again, we will look at their classification. There is not much about them, but of course, to understand this, of course, are also drugs that are important, especially again when you want to do, just like you want to do an investigation, you can use these drugs to relax the muscles. Centrally acting muscle relaxants, they reduce skeletal muscle tone and are used in the treatment of muscle spasms of local sprains, lumbago, spasticity and spasms. Also relieve pain and spasms associated with fibrositis, bursitis, spondylitis, and muscle injury. So they can bring about muscle relaxation. And sometimes there are people who have a lot of muscle pain for one, sometimes because of viral infection, and because of bacterial infection. You can also have a sprain, and you can use they also relief, so they can be used for pain relief. Centrally acting muscle relaxants that are widely used include baclofen, cyclobenzaprine, carisoprodol, methocarbamol, clofencin, chlorzoxazone, ephedrine. Ephedrine, not it's a drug that we have come across under the antihistamine H1 blockers, H1 antagonists, and diazepam. And you can remember its difference methyl group at ortho position, and then diazepam. Mode of action: centrally acting skeletal muscle relaxants selectively depress the CNS, so they do have selectivity. They depress the CNS that controls muscle tone and suppress motor impulse transmission and suppress motor impulse transmission in the interneuron synapses of the CNS. So the advantages they will not depress the whole of the CNS, because if they depress the whole of the CNS, they will also cause sedative. They will also cause sedation. They will also can cause sedation. They can also cause sleep and so on. So the advantage we are seeing here is that they are indeed selective. Some of them, like we have talked about diazepam, we know drugs like diazepam will also cause our sedative hypnotic. So they will not only, drug like diazepam will not only cause the muscle relaxation, it will also cause a bit of sleep. I'm trying to put off my phone. So, but of advantage is what we have said, that they are selective. They selectively replace the CNS that controls muscle tone. So they are more onto the muscle and not to the other. Press the motor impulse transmission, and therefore are more selective for the skeletal muscles. And then they reduce muscle tone by selective action on cerebrospinal axis. They depress the spinal and supraspinal reflexes of the muscle tone. They depress the monosynaptic and polysynaptic reflexes of ascending reticular formation. Wakefulness is disturbed. In other words, they will still cause sedation, decreased anxiety, and painful spasm. So they will cause a bit of sedation. They will cause anxiety, and of course also they will decrease the pain which is brought about by spasms. The biggest advantage is that they have no effect on the neuromuscular junction, but reduce upper motor neuron spasticity and hyperflexia. So the biggest advantage is that they are not neuromuscular junction blockers, because if they were, then they would bring us a lot of toxicity. And that's why we have said we do have an advantage with these drugs in that they have selectivity. They might of sedation, they might of course they will relieve anxiety, but their major selective activity is reduction of the muscle tone and reduction of the pain. We can classify them into various categories, as we have done always. And we have the first category is glycerol monoethers and derivatives. Glycerol means the structure. You look at the structure of glycerol, and then you derivatize glycerol monoethers and derivatives. The structure of glycerol in the glycerol monoethers and derivatives. And in this category, we have mefensin, which we can say is a prototype. Then we have clofencin. From that name, you can see it has a chlorine group. And then, of course, it's a carbamate, which means this is an alcohol. It has been carbamylated to give us the carbamate. And we also have the methocarbamol, which you'll see has a slightly different structure, but it's also a carbamate. Then you have the second category, which is and derivatives. Again, it means you have an alkyl and two alcohols. So you have an alkyl group that is attached to an alkyl group, which is attached to two hydroxyl group and derivatives. And under that, we have meprobamate, carisoprodol, which we have said has good activity, taxolone, and lobamate. Some of them, like meprobamate, is no longer used for some of these purposes, because it was found that it also causes sedation, and indeed it's also addicting. So it's a match, because as we have said, although they are selective, they still have some effect in the CNS, causing sedation, and therefore, and of course, sometimes when they cause sedation, it means they can also cause sleep, and sometimes it can be addictive. We have the benzodiazepines, which indeed we have discussed, like diazepam. So again, the SAR of the benzodiazepines will apply here. We have looked at the benzodiazepine, and mainly for the purpose of that compound crossing the BBB. And of course, you can see diazepam, a very common drug, and we have a new molecule there, but it is a benzodiazepine fluticasone. It's just the substituents on the ring that are different. Then we have the benzazone, where we have clozoxazone, and if you look at some of your pain medications, in some of the pain medications, you will find additive or added as a combination. So you could have even paracetamol, clozoxazone, because the clozoxazone, we are saying it will relax the skeletal muscles centrally and cause less pain. It will relieve the pain through relaxation of the skeletal muscles. Then you have the GABA receptor agonist. GABA receptor agonists, and we have baclofen. Again, remember, GABA receptor agonists, they in nature. Remember, GABA receptor agonists will be inhibitory. GABA itself is inhibitory, and of course, even the benzodiazepine act through the GABA receptor. So GABA receptor agonists are also inhibitory, and of course, once they are inhibitory, of course, these ones are binding the GABA receptor. The benzodiazepines bind an allosteric receptor. That is quite a difference. But of course, they are inhibitory, bringing about release of chloride ions, which is inhibitory, and therefore, again, depressing transmission. We do have also the tricyclic unrelated compounds, and we have the cyclobenzaprine, and TCAs and related compounds. Then we have miscellaneous, where of course we have phenadrine, and we had mentioned it, and we have dantrolene, which indeed also is used as an antidote in case you use a lot of halothane. In case you get halothane, where you can get hypothermia. In case you have halothane toxicity, you can also use dantrolene as an antidote. It is also used as a muscle relaxant. So those are the several classes. As I have said, although they are not quite a number, they are simple. I don't have too much on them. So we have the first category is glycerol monoether and derivatives, and we have mefensin, which we have said is the prototype, and the other congeners or the other derivatives. So you can see we are calling them glycerol, and you can see here, this is our glycerol there. In all of them, we have that molecule. All of them will have that. Of course, this is a carbamate, so being a carbamate, it was ending here. So all there. And then you do carbamylation. This was for carbamate, so it's coming there, and again ending there. So you can see that's our glycerol moiety, and that's why we are calling them glycerol. And then you can see monoether. This is our monoether there. Monoether. So they are glycerol, and all of them actually have the whole of this group. So if you look at them, all of them have the whole of this group. The only thing that has happened, some of them, there is derivatization of the alcohol into the carbamate. And once, of course, you derivatize the alcohol into the carbamate, remember this one has much higher polarity. You metabolize it into the carbamate. The carbamate is stabilized through resonance. This we have done before. It is much, much more stable. It has less polarity, and therefore much, much better lipid solubility, and hence better activity. But of course, it could be cleaved in the body to give you the active compound, but it has more stability, it has higher lipid solubility, and therefore better activity. So you can see you have mefensin, chlorphenesin, and methacarbamol. Those are three good representatives of the glycerol monoether and derivatives. So if you look at mefenecine, we can say not used systemically, as it is an irritant rather than a reductant. If you use it systemically to irritate the system, and therefore you can only use it topically. Used as a topical application, acts centrally at the cerebrospinal axis. And of course, even when you use as topical, remember you do have a lot of blood vessels. So it even used topically, it has good absorption. That's what we are saying. You use topically, it will be absorbed and it will get into the brain, acts centrally at the cerebrospinal axis, as we have said. It reduces, as we have said, neuronal excitability, leading to decreased action potentials to muscle fibers, which ultimately produces a reduction in spasticity. It has been observed to block both inward sodium and inward calcium currents in the neurons. So in other words, it kind of also is acting as a calcium gated, and so it also seems to block the calcium gated and sodium gated channels. The synthesis, as I have said, basically there's not much on this synthesis of this, and you can see we are starting with 2-methylphenol. Of course, when you look at these groups, that subsequent and that subsequent, there is the order of priority. And if you have a methyl group and you have an alcohol, alcohols have a higher order of priority, so therefore we name that compound as a phenol. When you have a methyl group and a hydroxyl group, of course, ortho substituted to, both of them ortho substituted to a phenyl group, that compound, we also call it ochrysal. So the methyl group, hydroxyl group, ortho substituted, we call it orthochrysal. So you can either call it 2-methylphenol and you add 3-chloropropane, 1,2-diol. So we are starting again. Remember, alcohol has the higher priorities. We can say 1, so the position 1, 2, 3. So the chlorine group is at position number 3, and the alcohol is at position 1 and position 2. So 3-chloropropane, again, you look at the longest chain, it is 1, 2, 3. So 3-chloropropane, 1,2-diol. And this almost is, of course, this is almost the compound we're using more throughout. So 2-methylphenol, 3-chloropropane, 1,2-diol. With removal of hydrochloric acid, you get your mefenecine. So alkylation of ochrysal with 3-chloropropane, 1,2-diol affords mefenecine. Metabolism. Readily metabolized to its major metabolite product, the toluene. Toluene means from toluene. Toluene oxylactic acid. Toluene oxylactic acid. Toluene means you do have a lot. Toluene group is a benzene ring with a methyl group. Toluene oxylactic acid, which is inactive. Mefenecine carbamate or succinate derivative. The mefenecine carbamate, all the succinate derivatives show longer duration of action than mefenecine, although less active than the parent drug. So we are saying once you carbamate or you add the succinate, those derivatives, they have much, much better activity. So that's how mefenecine, and the only difference is that this compound group here, that's all that's happening. You see, this is an alcohol dehydrogenase, and it is oxidized to the aldehyde and then oxidized to the carboxylic acid. That's all that has happened. So you start with that group there, further oxidized to the carboxylic acid to give us an M-toluene oxyl acetic acid. That is a major metabolite. Then we look at the other one, is the chlorphenecine carbamate. So again, from the name, you can see it's no longer mefenecine, it's chloro, which means there is a chloro group which has been introduced. And you can see this time you have a chloro group para to the hydroxyl group. The other one was a meta group. It was meta methyl group. So methyl group, ortho to the hydroxyl group. But this time, of course, the chloro group is para to the hydroxyl group. Do remember, whenever you introduce a chloro group in a benzene ring, you have decreased metabolism. You decrease the metabolism because you might block the position of hydroxylation. And of course, also, you do remember halogens also increase the rate of they increase the lipid solubility and therefore the ability of that molecule to cross the BBB. So you have those two characteristics added. One, you have decreased, more often than not, you decrease the rate of metabolism because one, the chloro group decreases the electron density, it decreases the electron density, or it interferes with the delocalized electrons, decreases the concentration of the delocalized electrons, and therefore decreases the rate of reactivity of the benzene ring, including oxidation. So that is one. Number two, halogens in themselves add increased lipid solubility, so they will increase the lipid solubility of that molecule, and that compound will be better absorbed. Also, depending on the position where you have put the halogen, you can actually block the site of metabolism. So not only will the halogen decrease the rate of metabolism, it can also block the site of metabolism, and once it blocks the site of metabolism, then again decreases the rate of metabolism, and therefore that compound will have a longer duration of activity. So halogens are known to have a lot of activity. They, of course, withdraw electrons through inductive effect. They push in electrons through resonance, but the inductive effect is predominant, and therefore they will deactivate the ring through inductive effect. But they will be what we had said earlier, orthoparadielectors. Whenever you have a chloro group and there's something coming in to be an orthoparadirector, although it is a ring deactivator, it also can block, depending on where you put it, you can block the site of metabolism. So as I said, that this, you are using the same reagent, the 3-chloropropane, 1,2-diol. Remember, all of them are glycerol derivative, so you're using the same derivative, and of course it comes and joins at that position. So you lose the chloro group, you lose that chloro group there, and the CH2 is joined, adds on to the oxygen, and of course then you lose phosgene. So the first one, you lose hydrochloric acid, then you add phosgene. This is an addition you are adding. So you add phosgene again with loss of hydrochloric acid, and that will give you up to, you are here CH2O, the phosgene will add here. So this is the phosgene which is adding there. Phosgene adds there, and of course you can see you still have a terminal chloro group which is very readily replaced, and you react with ammonia and loss again of hydrochloric acid to give us the chlorphenazine carbamate. And you can see that chlorphenazine has again two advantages. It is a carbamate, unlike mefenazine, and of course it has a chloro group. So that is the process alkylation of the 4-chlorophenol with 3-chloropropane 1,2-diol, followed by reaction with phosgene and ammonia with loss of hydrogen chloride affords chlorphenazine carbamate. Of course, a step ahead, whereby we have, of course, substitution with a halogen, and of course carbamylation of the glycerol. Mefenazine is weakly active and short-lived because of the fast metabolism of the primary hydroxyl group. Carbamylation of this group increases activity. So we carbamylate, we block that site of metabolism. We also stabilize that the resultant compound, the carbamate, has been stabilized by resonance, and we say amides are not as readily hydrolyzed, and therefore the compound has a longer duration of activity. Chlorination increases lipophilicity and seals off the para position from hydroxylation. This we have already said. So it will increase lipid solubility, better absorption, blocks the para position, decreases the rate of metabolism through negative inductive effects, and therefore again increases the duration of activity of the chlorphenazine carbamate. Metabolism is still fairly rapid and involves glucuronidation of the second hydroxyl group. So you still have one hydroxyl group of the secondary hydroxyl group. You have carbamylated this, you still have your secondary hydroxyl group. Although it's a bit hidden, it can still undergo that secondary. It can do this hydroxyl group, though a little bit hidden than the primary one. The primary one is the one which is attacked first. And then, of course, you are still saying glucuronide conjugation of the secondary hydroxyl group can still occur, and that's why we are saying that the metabolism still fairly rapid involves glucuronidation of the secondary hydroxyl group. What are the uses again? It's used to diminish skeletal muscle spasm resulting from osteoarthritis and vertebral disc syndrome. Again, that is a dosage which I believe you will look at in pharmacology. The next one is methocarbamol. And as you can see, this is our structure of methocarbamol. Again, the major difference is that we have a methoxy group at the ortho position. Remember, because of this oxygen, this compound here is an ortho para director. So again, that methoxy group will block that position of metabolism, of course, although the para position is the one which gets more metabolism. Of course, in addition, do remember that so this blocks the ortho position of metabolism, and of course, there's carbamylation, as you can see there, carbamylation, and that again increasing activity. So synthesis is similar to chlorphenazine carbamate with 2-methoxyphenol as starting material. So the only difference here is the starting material, which is different because you must start with 2-methoxyphenol. So here, this must be a hydroxyl group. So 2-methoxyphenol, again, when you have methoxy and phenol and a hydroxyl group, the phenol still takes first priority. So the compound is named after phenol, and the methoxy group is again alkylation of 2-methoxyphenol. Again, this compound remains the same for all of them, followed by reaction again with phosgene and ammonia with loss of hydrogen chloride, because we are going to do carbamylation. And for you to do the carbamylation, you do require to add the phosgene, and then you lose your hydrogen chloride. Methocarbamol is also a mild muscle relaxant for minor musculoskeletal spasms or in patients who are intolerant to stronger muscle relaxants. Its uses can be used in Parkinsonism and also in cerebrovascular misshapes, and those it can be used also. IM can be given IM in case the patient, it can be given intravenously, and also it can be given IM intravenously 1 to 3 grams per day, administered at a route not exceeding 0.3 grams per minute, or by IM 1 gram every 8 hours. So that, of course, gives us the methocarbamol an advantage in that you can give it parenterally, and of course you give drugs parenterally in case of the severity of the problem, or if you have issues of oral administration, like perhaps the patient is vomiting or such things, then you can go for the parenteral administration, and again, this depending on the severity of the condition. The SAR, we have mentioned quite a bit of it. The other substituted benzene derivatives are generally more potent than the corresponding para or meta isomer, and we have methocarbamol. So we are saying, if you look at mefenecine, you have, see that one is an ortho derivative apart from, cause chlorphenazine, which is a para derivative. Again, if you look at mefenecine, it is also an ortho derivative. So we are saying the ortho derivatives for these groups, and for the methoxy group and the methyl group, ortho derivatives have showed much more activity than putting those subsequents in the para position. Again, when you look at those, the methyl group and the methoxy group, you can see they are groups that are subject to metabolism. But when you put them in the ortho position, there can be steric inhibitors introduced by the glycerol moiety. There can be steric hydrons, and therefore the accessibility of the methyl group or the methoxy group is less. It is restricted, and therefore that compound was found to have better activity. When you put these two groups in the para position, they'll be readily exposed to the metabolizing enzyme, and therefore a compound will be readily metabolized, and of course will have much lower activity. Also, substitution of a small alkyl group or alkoxy group in the benzene ring increases activity again. So we have said the first one, they should be in ortho position, and if you add a small alkyl or alkoxy group, and you have an alkyl group in mefedazine, you have an alkoxy group in methocarbamol, that increases activity, and that is why those drugs have one has a methyl and the other one has a methoxy. Carbamylation of the secondary terminal alcohol increases activity, chlorphenesin, carbamate, and methocarbamol. We have said 1, you have blocked the cytometabolism. 2, of course, you have increased the lipid solubility because that resultant compound is stabilized by resonance. It is not as polar as the previous compound. Parachlorination increases also the lipophilicity and sees of the paraposition from hydroxylation. And that compound, this is only definitely in chlorphenesin. So they also tried putting a parachloro group in chlorphenesin, and indeed that compound was found to have good activity, and we know why. We had already explained. If you substitute the benzene ring with any other group, like hydroxyl group, an amino group, or an acetyl group, there is a decrease in activity. So the groups that are accepted are alkyl, alkoxy, also a methyl group. So sorry, alkyl like a methyl group, alkoxy, or a halogen, and those groups must be in specific position to maximize the activity of these compounds. That is the first category, which we are calling the glycerol monoethers and derivatives. The second compound group, is a substituted alkane diols and their derivative. You can see here is our alkane there. Alkane, and this is the hydroxyl group. So alkane diol. Metaxolone, so that is carisoprodol. And if you look at this, and then you have our alkane, alcohol there. Meprobamate, again, you have that there. Alkane, there. It is only that, of course, it's an alkane diol, and then it has been carbamylated. Again, you carbamylate to decrease the polarity, to increase the stabilization of that molecule. So you get rid of that group that is highly metabolized. You put a carbamate, and on carbamylation, the compound is stabilized by resonance. It is not also readily hydrolyzed, and it has better activity. You have also lobamate, which is not marketed. Again, you can see it has a lot of structural similarity with meprobamate, very close similarity with meprobamate. You can see it has also been carbamylated, and the only difference is the group on this side, which group you carbamylate it with. One of the hydrogens here has been replaced with a cyclic group, a cyclopropyl group with retention of activity, but unfortunately it's no longer marketed. If you look at carisoprodol, the group there is isopropyl group. If you look at this, of course, this has been carbamylated on both sides, so you have, and it is not substituted. So here you can see the amino group for carisoprodol is the one which is substituted with isopropyl, giving it, of course, much more lipid solubility, but you know these alkyl groups are also susceptible to metabolism. So when you look at meprobamate, that group there is not substituted. So those are the main ones, I think, that I was able to get: carisoprodol, metaxolone, meprobamate, and lobamate. Let me not get these codes again. We had already, of course, mentioned the general mode of action. I don't know why I've repeated it, but against two selectively replaces spinal and supraspinal polysynaptic preferences involved in the regulation of muscle tone. They do not significantly affect monosynaptically mediated stretch reflex, so you can still have your stretch, the reflex actions. They do not affect that. Meprobamate, there is a structure. Yeah, when we looked at it, it is also a metabolite of the centrally active muscle relaxant, carisoprodol. Look at carisoprodol. So can get oxidative N dealkylation. Oxidative N dealkylation there. If you get oxidative N dealkylation, then you will see. We started with each one. Yes, meprobamate is correct. oxidative and dealkylation. We will remove that, and this will become an amino group, and we will get our meprobamate. And that's why we are saying it is metabolite of the centrally acting muscle relaxant carisoprodol. It's addicting due to sedative effects, and therefore really rarely used for that purpose. Carisoprodol, it's a carbamate ester that is mono and isopropyl derivative of meprobamate, which is a main metabolite. So once it is metabolized, you can see it is metabolized. This is its synthesis. Of course, this is synthesis. I don't think I bothered to show the metabolism. It's a simple metabolism. This is synthesis. So if you are metabolizing, all you are doing again is here, oxidative and dealkylation. Oxidative and dealkylation of carisoprodol will definitely give you meprobamate. So it's ester and it's carbamate ester that is mono N isopropyl derivative of meprobamate. So you have the N isopropyl derivative, and you can see it there, CH3, and of course CH3, and of course that will also meprobamate, of course, as we have said, it will be the main metabolite on oxidative and dealkylation. It has 2 chirocenters and formulated as a reciproc mixture. If you look at it, this carbon here, that there, for sure is a chirocenter, because it will have a C, you have CH, it will have 2 CH, so that cannot be a chirocenter. The other chirocenter. This is one chirocenter there, for sure. It's CH3, which is our other chirocenter. One chirocenter there is our other chirocenter here now. CH, because these are the same. This is CH3 too. Let me look at it on the other chirocenter. I didn't even look at it. Yeah, okay, because this cannot be a chirocenter. You can see that here, because that's a CH3, that's a CH3. It has this chirocenter here. Actually, I can't see the other chirocenter. That's one chirocenter there. Can't see any other chirocenter. I don't know which other chirocenter they are talking about. Because this is not a chirocenter there. Because it has a methyl group, and it has a methyl group, so it cannot be a chirocenter. This is the only chirocenter I can see, but I'm going to find out. But I can really not see any other chirocenter. Because all these other groups are not chirocenters. I didn't check up that. I'll check it up. But I can only see so far only this chirocenter here. Because a chirocenter is that carbon which has 4 different substituents. This does not have 4 different substituents. There is no other carbon there. I don't see. So perhaps it was meant for something else. So I will check that up. I'm sorry about that. I'll check that of the 2 chirocenters, because even you, when you look at this structure, you cannot see 2 chirocenters. I think that person mistook and say that one's a chirocenter and it's not. So, but I'll check it up and confirm. So the other one we had looked at is metaxalone. And if you look at its structure, so it's, again, it's of course whereby one of the alcohols is part of a cyclic ring with retention of activity. So again, that is the way you synthesize it. I said some of these are very brief. So that gives a summary of the compounds or the general anesthetics that under that compound of alkane diols. So as I say, there is not much somehow. Even as you look for this compound, there is not much on them. Then we have another class which we call the benzazoles, and the benzazole, the chlorzoxazone, as I have said, it's a very important drug, and I've seen it mainly in combination. You find it in combination with other painkillers like paracetamol, and you find chlorzoxazone in combination as a muscle relaxant, again to help in any of the muscle pain. Again, it is synthesized by heterocyclization, reaction of 2-amino-4-chlorophenol with phosgene. That's phosgene, and this is 2-amino, starting that position 1, 2-amino, 3,4-chlorophenol. So 2-amino there, 4-chlorophenol, and you do cyclization, heterocyclization, meaning, of course, you are adding the hydroatoms with phosgene, and you can see that is a resultant compound. So you have that, and this amino group there, and the hydroxyl group are the ones which this was our former. This is a C double bond. So you lose these 2 chloro groups there, and the carbonyl group joins the amino and the hydroxyl group, which was found in the phenol. So that is our our cross-soxazone. And as I have said, a very good compound, and normally you find it in combination. It is another mild muscle relaxant that is not as strong as the carisoprodol or cyclobenzaprine, and is also less sedating. And I have said it's a very good one in combination. Use the skeletal muscle relaxant for the reduction of pain, muscle spasm, such as myositis, sprains, and acute or chronic back pain. And this was myositis and myositis, or I think it's supposed to be myositis, is a name for a group of rare conditions. The main symptoms are weak, painful, or aching muscles. I think it's supposed to be myositis, not myositis. I think the C is not there. Myositis is the name of a group of rare conditions. The main symptoms are weak, painful, or aching muscles. And we are saying you can't be able to give chlorzoxazone. And sometimes it is even given, as I said, in combination with other drugs like paracetamol. And in case you have a lot of muscle pains, and sometimes you find that you have backaches, you have back pain, and you can be given this drug in combination with other ordinary painkillers like paracetamol to take care of that back pain. As we have seen, chronic back pain, muscle spasm, can use that drug. And if you when you go out there, already you've been out there, and I hope you are able to look at some of those combination formulations for analgesics, and you'll find it is one of them. Then we have the heterocyclic bases. Of course, these are one class is the benzodiazepines. And for benzodiazepines, we had said diazepam. Everybody I know can be able to the structure of diazepam. And then we had fretazepam. And you can see the only difference between fretazepam and diazepam is a substituent at position 7 is the same as that found in diazepam. So the difference is a substituent at position number 1, where of course diazepam has a methyl group, and at that position it does not have any substituent. So that's the only difference. And you can see again, we do have a lot of floral groups. I bet to improve on the lipid, increase the lipid solubility, decrease the rate of metabolism, and of course that drug penetrating the BBB and joining and binding the respective receptors within the brain. And what this drug specifically gives us has more. It will have the others like sedative, hypnotic activity, but it's one of the benzodiazepines which has much more muscle relaxant activity. Remember when we were looking at benzodiazepines, we did mention that the major disadvantage of benzodiazepines is that they are not very selective in their choice of receptor, and they can bind many receptors. And I remember saying one of their activities is muscle relaxation, but they will bring the muscle relaxation, it will be minimal. But this particular drug, the fretazepam, was found to have much more. On addition, on the structural substitution, on the structural modification of diazepine to give us fretazepam, where you have the trifluoroethane group, trifluoroethane group at position number 1, and we have a fluoro group and a chloro group at position number 7 and position number 2 prime respectively. That drug, which is fretazepam, was found to have much higher muscle relaxant activity. And as I said earlier, the other SARs will happen, whereby we are saying that the drug will obey those other SARs that we had mentioned, especially for purposes of penetrating the BBB, get into the brain, and give us that kind of activity. The other heterocyclic base is nefopam. Again, you can see this one is not a complete benzodiazepine because at the position number N, you have a methyl group. So the phenyl ring at this position here is replaced by a methyl group. And then this is 1, 2, 3, 4, 5, 6, 7. So 1, 2, 3, 4, 5, 6, 7, 8. So this also is an octane ring. So of course a heterocyclic, it's a ring which has, it's not really octane, but it's a ring we can see which has eight atoms because it does not have carbon alone. It's a heterocyclic ring containing 8 atoms, and we know the benzodiazepine is a heterocyclic ring containing 7 atoms. So that, of course, also differs. Of course, we have our benzene ring and this position. So it actually is just reversed, sorry. So even the nefopam is also, it's not a benzodiazepine because we are saying for benzodiazepine that should be a 7-membered ring, but I've noted that it also has this ring. It's a C6H5. Then in its ring, it's 8-membered, and then in place, you see this one has 2 nitrogens, but the nefopam has an oxygen as a nitrogen, and it's an 8-membered ring. It's an 8-membered ring, and that's why we, instead of calling them benzodiazepines, we call them heterocyclic bases, so that also nefopam can also fit in that group. Of course, the benzodiazepines, as we said, will be fluticasone and diazepam, and of course now when we classify them as a heterocyclic bases, then we're also able to put nefopam there, and the nefopam, again, you can see has here nitrogen with a methyl group. It's very similar to what we have for diazepam, and it has that group there. It does not have any of the halogen substitutions as compared to the benzodiazepines, but it still has very good, because I think that's why we have increased its ring to 8 members, so that we increase the number. We try to compensate for the lipid solubility. That compound will still penetrate the BBB and bring about selective depression of the spinal cord. Mode of action of the benzodiazepine. These drugs produce centrally mediated skeletal muscle relaxation by acting on the benzodiazepine receptors in midbrain reticular formation and on the limbic system. So, as we said last time, the benzodiazepines are not highly selective for their receptor. You know, they will bind the GABA receptor to bring about sedative hypnotic activity. And of course, even when you give them here, they will still bind the GABA receptor to give us sedative hypnotic activity, and therefore they will be responsible for some degree of activity of sedation. But for the muscle relaxant activity, they are binding the benzodiazepine receptors in the midbrain reticular formation and on the limbic system to bring about muscle relaxation. So they will still bring about depressant activity in these areas. It's only that the receptors are in a different area. The receptors are not the GABA receptors. The receptors in a different area, binding in the midbrain reticular formation and on the limbic system. It acts on the it's still acting. It's still actually, even in these centers, it's still acting on the benzodiazepine receptor. That's the GABA allosteric receptors, increases it. So it is acting the same as in causing sedation, interestingly. But I think it's the area where it acts. I believe, I'll again confirm that, but I believe the area, the center, the site where it is acting, I believe is where it is different. So it's acting in the midbrain reticular formation and on the limbic system, where it still acts on the benzodiazepine receptor, GABA allosteric receptors, increases the chloride influx inhibitory action, as we had said earlier, produces hyperpolarization, decreasing the firing rate. Remember, we had mentioned when we compare benzodiazepine and the barbiturates, the benzodiazepine decrease the firing rate, whereas the other one increases the duration of the opening of the channels, inhibits the calcium-dependent release neurotransmitters. So it is still acting, sorry about that, it's still acting in the same manner. I believe that what is different is the location of the location within the brain where it's acting. is acting within the midbrain, reticular formation, and the limbic center, and still binding the GABA receptors. And as we had said earlier, the GABA receptors, we know they're inhibitory. Of course, also they will bind allosteric. They bind allosteric benzodiazepine receptors, which have an influence, which have the same activity. They have the same activity as binding the GABA receptors, although these are allosteric receptors, releasing chloride ions, and as we had said earlier, chloride ions are inhibitory, and therefore, again, bring about a decrease in motor neurostimulation. And then there's the synthesis pathways. The next one is the GABA agonists. And under GABA agonist, we have the baclofen. And the baclofen, this is the structure of baclofen, not very complex. Structure here, I believe, of baclofen. So you can see 1, 2, 3, 4, 5. It's like you can see this, like to me, is like gamma aminobutyric acid, and it is substituted at that position. So, but this one is, this is the beginning of formation. So this is its mode of the synthesis of baclofen. That's how it's synthesized. Useful in treating spasticity associated with spinal cord tensions, as in multiple sclerosis. That it's dose. I was thinking I would say something more about it, or I'll look for something about it. But I think it has some link. I didn't say its mode of action. I'll check up its mode of action, because this is looking like 1, 2, 3, 4. A gamma aminobutyric acid. So I'll look up its mode of action so that I'm very sure whether it has any link with, in the case it's a GABA agonist, So it's a GABA agonist, it's going for, it's a, no wonder you can see the structural resemblance there, because GABA is gamma aminobutyric acid. So you can see the structural resemblance with GABA itself. And of course, the gamma aminobutyric acid is substituted at position 2. So you can see it is 4 amino, 3 chlorophenyl butanoic acid. So there is some structural resemblance of baclofen with GABA, and therefore this drug can, of course, go for the GABA receptor. Then, of course, you see that there's a huge substituent. There is a bulky substituent. And as compared to GABA, or as compared to GABA or gamma aminobutyric acid, there is, of course, this substitution, and that substitution, which is, of course, the phenyl ring, which is chlorosubstituted, giving that compound much higher lipid solubility, giving that compound also a metabolic stability, and so on. So that there's a main difference. But you can, and of course, when you have these big groups, normally they bind, as we have said, out more often than not. They don't normally go for the receptor. They bind outside the actual receptor. But once they bind outside the actual receptor, they give anchorage. They anchor this molecule well onto the receptor. It fits well. Of course, it's not an antagonist and an agonist, but it binds well, fits well, and can be able to stimulate the receptor to give you the same activity. And of course, if it has GABA-like activity, it will act as a neuro. It will have inhibitory activity. It will have inhibitory activity because we know GABA receptors have inhibitory activity. So I think that's why, although I didn't put any note towards that, it's important to see that when we look at that structure, it had a structural similarity between baclofen and gamma aminobutyric acid, so that this drug, baclofen, can effectively compete with, it's not really competing, but it's going for the GABA, it's an agonist. It will go for the GABA receptor. Fortunately, it has agonist activity. It has structural characteristics that give it high lipid solubility, so a lot of concentration in the brain. It has also the Bark group, which can bind adjacent the GABA receptor to anchor that molecule properly. The molecule, fortunately, has intrinsic GABA activity, and therefore it will bring us the inhibitory activity, which we do require for the management of what we're calling the spasticity or other muscle conditions. Then we have the TCA and related compounds. Remember, the TCAs are tricyclic. We call them TCAs, and the TCA means tricyclic antidepressants. And I think we did mention the tricyclic antidepressants, the imipramines, the which other one did we mention? We did mention imipramine, amitriptyline, and so on. So we did protriptyline, imipramine, mipramine, and so on. So there were quite a number, and we call them tricyclic because they have this structure here. That's the tricyclic there. Actually, should just, I think it would be tricyclic and related compounds. I don't think the A should really be important. What's more important is that they are tricyclics and related compounds. But you can see, like, this one is, I would expect this compound to have antidepressant activity. I think that's why they're calling them tricyclic antidepressants. So we have the first one is clobenzapine, and you can see the compound here, there. It has very slightly different from the tricyclic antidepressants. Remember, we did like amitriptyline. We either had, like, this one has the endocyclic bond and the exo bond, the endocyclic and the exocyclic bond, and of course this is a benzene ring. That's a benzene ring, and that's the only difference, that it has that bond there and it has that bond there. It has the two bonds, but you can see CH2 and so this, you'd expect it also to have some antidepressant activity. It has actual structural similarity with the structural antidepressant. And I think that's why we are calling them tricyclic antidepressant and related compounds. So you can see cyclobenzamine, very, very similar structure, double bond there, and so on. Muscle relaxant has been shown to be beneficial in fibromyalgia. So that is the structure there. Then we have the next class. So in that class, we have only one. Then the miscellaneous, where we said we have dantrolene and you have ephedrine. In case I get any more details for any of those compounds, like, I think I'll try and check something a little bit more for this cyclobenzapine, in case there is any more. Maybe something little. So the miscellaneous is dantrolene and ephedrine. As we have said, ephedrine is not new to us. Ephedrine is a compound that we discussed when we were looking at the antihistamines, and we did mention that the ephedrine does not have much of the antihistamine activity because of the ortho methyl group, which influences the structure that you require, the size. Remember this, we are talking about a specific size which is required to bind the antihistamine receptors. We have dantrolene, and if you look at dantrolene, you can also see it's an imidazole derivative, imidazoline derivative. This is the one we are calling the imidazoline, and we are calling it imidazoline because when we talk about imidazole, there will be a nitrogen there, because always make sure that they go in. It's hard to draw with this pen for sure. And then normally this one has a hydrogen, if you remember, at position 1 of when we look at the imidazole, and we will have a double bond there, and we'll have a double bond there, right? So the imidazole has the two double bonds. So once, if you look at this, it is devoid of the double bonds, and that's why we are calling it imidazoline. So imidazoline does not have the double bonds, and that's why we are calling it an imidazoline derivative. So you can see that it has that imidazoline derivative. It has the pyrazole, the furan ring. So that is a imidazoline ring there. It has a furan ring there, and of course it has a benzene ring there. So it's also not a very difficult molecule. You remember imidazoline, and then it has a furan ring and a benzene ring. So that's dantrolene. And again, I didn't mention, very important antidote also in case you get halothane hyperthermia, whereby if you get halothane toxicity, you can give dantrolene as an antidote. That it's synthesis and the mode of action and metabolism. Again, as we have said, it does not affect the neuromuscular junction transmission of membrane action potential, which is very good. It works by blocking the release of calcium from the sarcoplasmic reticulum of skeletal muscle cells by acting on the ryanodine receptor calcium channels. So again, therefore, you remember it blocks the initial release of calcium ions. So it blocks the initial release of calcium ions, and once it blocks the release of the calcium ions from the sarcoplasmic reticulum of the skeletal muscles, then it will have an influence on the total release of the calcium. It will have the calcium, remember, comes from the sarcoplasmic reticulum. So that is where it acts, blocks the release of that calcium, and therefore it will block the availability of the calcium within all the skeletal muscles, and hence bring a result in inhibition. Inhibits excitation. It also inhibits the excitation, contraction, coupling in the muscle fiber. So it also inhibits the excitation, contraction, coupling in the muscle fiber. Remember, when you have the muscle, you must have a contraction, and then you have relaxation, alternating relaxation, contraction. So it also inhibits that coupling, and therefore will not allow for muscle contraction to occur, and hence the muscles will relax. Then it is a drug of choice for the treatment of malignant hypothermia crisis. This malignant hypothermia crisis is the one I'm talking about, which is caused by halothane. So if you have a person who, remember we talked about repeated use of halothane can be highly toxic. So for some of the people, not all people, can be toxic, and it can cause the malignant hypothermia. Dantrolene has been found, because this malignant hypothermia has a lot of shivering. There's a lot of shivering, a lot of muscle contraction, and therefore it is used in that malignant hypothermia when you have toxicity towards halothane. It crosses the placenta and can be detected in the fetus after maternal administration. It's slowly metabolized to give 5-hydroxy acetamide metabolites. Formation of hydroxyamine during the metabolic process may be associated with liver injury. We are going to look at that. So it's a very important, at least you can see it has a slightly different mode of action also. It's going for the release of the calcium from the sarcoplasmic reticulum, and therefore overall it is able to have a negative effect on the muscle relaxation contraction process. Then it's available for intravenous use in vials containing 20 milligrams lyophilized dantrolene sodium added to 3 mannitol to improve water solubility. So the mannitol in its formulation, you have of course discussed what lyophilized is. That is pharmaceutics. I believe you have done a lot of that. So it is given in vials as available for intravenous use in containing 20 milligrams lyophilized dantrolene, but you have sodium added to 3 grams mannitol to improve. This is definitely a sugar. You know, sugars have a lot of hydroxyl group, so that will increase its water solubility. Used for the control of the spasticity resulting from spinal cord injury, stroke, and multiple sclerosis. And of course, we have also said it can be used for malignant hypothermia or halothane toxicity. It is, as we have said, given IV, and that is why we require it to have a lot of water solubility. We did mention about its toxicity when you get the hydroxylamine derivatives. Let us look at how it's metabolized. So we have the dantrolene, and of course we have, say, plus mannitol, and it is absorbed. So it's dantrolene sodium. It is absorbed to give us the dantrolene free base, and the dantrolene free base Canada Gore reduction. You can see this. You look at it, it is a nitrophenyl group. There's a nitrophenyl group, and you know any a nitro group attached to a phenyl group, Canada Gore reduction or by nitro reductase. Canada Gore reduction by nitro reductase to give us an amino group there. So that's the first one. It's just the structure of the whole of the dantrolene undergoing nitro reduction, and the resultant there is an amino group there. So that gives us aminodantrolene. Then it can also undergo hydroxylation, and of course, when it undergoes hydroxylation, and see that one remains. Let's see the hydroxylation. 5-hydroxylation, here we are. So the imidazoline group can undergo hydroxylation at this position there. Remember, this is position 1, position 2, position 3, position 4, position 5. So it's undergoing hydroxylation at position number 5 to give us again 5-hydroxydantrolene. So on the imidazoline group, undergoing hydroxylation. Remember, hydroxylation is catalyzed by cytochrome P450 enzyme. It's an oxidative process. Then when you get the aminodantrolene, this amino group, in many cases, when we are looking at this, the sulfonamides, we did say whenever you have an amino group readily acetylated, of course, catalyzed by N-acetyltransferases. You catalyze the addition of or the acetylation of the amino group. And remember, we did mention, I believe you do have done metabolism, acetylation usually does not necessarily increase the water solubility, but it is important for termination. It's important for termination of the pharmacological activity, not necessarily increasing water solubility. And that's why we did mention, even for some of the sulfonamides, whereby they have very low water solubility, when they undergo again acetylation, there is even further reduction in water solubility and crystalluria. So that again, we are reminded here, acetylation for termination of the pharmacological activity, and that gives us, of course, the acetyl-aminodantrolene. Then we are saying that this compound, the aminodantrolene, can also undergo further oxidation. Can undergo further oxidation. If it undergoes further oxidation of this group, and that group becomes NH. NHOH. If the amino group undergoes oxidation, further oxidation, and you get this is oxidized, so one of the hydrogens is replaced by a hydroxyl group, you get what we call the hydroxyamino, the hydroxyamine-dantrolene, and this group is known for toxicity. Hydroxyamine group, and you remember even when we were doing again the sulfonamide, we said one of the routes of metabolism to give the hydroxyamine can result in cytotoxic intermediate or reactive metabolite. So that's the only way that this drug can cause toxicity. It can cause toxicity when it's metabolized to give it hydroxyamine, because hydroxyamine is responsible for cytotoxicity, whereby this compound can bind groups within the body which have low or which are electrophiles. This group is rich in electrons. It is a strong nucleophile which can bind groups that are poor or have low level of, or which are electrophiles. So that is the metabolism of dantrolene. either by nitroreduction, nitroreductase enzyme to give us the aminodantrolase, which can also undergo further oxidation to hydroxyamine, which can bring about cytotoxicity, acetylation, resulting in termination of activity, all, of course, hydroxylation of the imidazoline ring to give us hydroxyimidazoline, 5-hydroxydantrolene. So that is metabolism of dantrolene. And I think with that again, I am done. As I've said, the only drug I've said I will check a bit. I'll check the class of the TCAs and derivatives. I'll see whether I can get any slight information. TCA and derivatives, let me note. Also check whether I can get, I doubt I can get anything else on baclofen. But for that, basically is the muscle relaxants. Any question? Are you going for when are you breaking for these elections? There's a lot of confusion. Is there any communication that you're having a break, Jacinta? Not Jacinta, but Frida? Can you communicate on the public chat so that we know? They're supposed to do a cut on Friday, the cut on anti-cancer drugs. Only the anti-cancers I will just give the anti-cancers, the second cut will be on the rest. Is there any or any word about you being in college and whether you are breaking for the elections, and if you are, when? I need you to continue reading seriously on narcotic analgesics. Quite a number of you, I'm looking at your papers, a number of you have still not got the concept properly. Some very good, some doing very well. But we need to be able to differentiate morphine from the morphine and derivatives, from the codeine and derivatives, from the morphinans, from the benzomorphans, from the 4-phenylpiperidines, and of course also from the propylamines. And we didn't need to understand that. At least we need to have to know the structure of each of the prototypes. And if you get the structure of the prototype, then you're able to get the other structures, because there is very minimal structural modification of the prototype. Of course, there was also the anilido phenylpiperidines, where we have the fentanyl and so on. So, and you need to understand what are the structural modifications that have been done in these compounds, so that they first retain the activity. Of course, for them to retain the activity, I think I only got one student who was very good and told me that, of course, if you look at those compounds, they obey the morphine rule. For them to be able to have an analgesic activity, one of the factors is that they obey the morphine rule. And once they obey the morphine rule, they have a quaternary carbon atom, they have a terminal nitrogen, they have a phenyl ring, which is separated, and so on. And we had discussed all these things. So the one of the characteristics of all those, either analogs or derivatives of morphine, of all those 4 classes or 5 classes, is that each group obeys the morphine rule. And then it has its now unique characteristics. Of course, we did mention the 4-phenylpiperidines. And we did mention the proteins, beta protein, alpha protein. Please master which is alpha. When you say alpha, what do you mean? What is the orientation of that methyl group? Some of you are confusing beta and alpha. And of course, once you confuse, you cannot be able to get your marks. And then, of course, all the way of the 4-phenylpiperidines to the antidiarrhea agents, the diphenoxylate, the loperamide. How do they define structure? And it's very obvious how they differ, although they have some structural similarities. Again, they do have structural similarities with the other morphine and derivatives, so that they can go for the receptor. That's important. They have structural features like the morphine and analogs, so that they can go for the mu receptor. But because of the fact that they have huge substituents. They have lipid solubility, they have very high lipid solubility, depoterization, and of course that is how you get them having, they have peripheral activity, and their peripheral activity that is pronounced is that they have antidiarrheal activity, which we know is a characteristic of the opioid derivatives, and fortunately, they are not able to cross the BBB to give us any binding within the brain, and therefore none of those toxic effects. Of course, sometimes you can get a small concentration and very minimal of the toxicity, and that's why no drug is safe. So please master narcotic analgesics by now. You should have them completely at your fingertips. You can draw any structure. And of course, when you are told an allele antagonist, there is only one. Most of you again kept confusing the name. You don't seem to know the difference between naltrexone and naloxone. One, of course, has a cyclopropyl methyl group. The other one is the one which has an allele. You confuse the names. Then, of course, we had mentioned when we were doing classification, we had mentioned all the different types of the classification as per their activity, and we had mentioned we had started with the agonists, natural, semi-synthetic. We had the mixed agonist, antagonist. We had the partial. Some of you, when I ask mixed agonist, antagonist, you give me the partial. And then also, if you look, I have asked as derivatives of morphine. So why you are giving me the butorphanols, I don't understand, because it is only nalorphine and nalbuphine, which are complete derivatives of, where you are changing the groups that we have on the morphine. You are not removing any ring. So those are the drugs that are expected as derivative of morphine, as analogs of morphine, which have agonist and antagonist activity, because of course they bind both the mu. They bind one with agonist activity, and they bind the morph and the K with antagonist activity. But the mu, of course, has better activity than the K, and therefore they are able to have both activity. So please master. That cut was very easy. I was expecting 100%. But most of you are not. You need to do a bit more reading, master those drugs. Don't confuse them. Understand what is the influence of any substitution on any position. What's the influence of any substitution on any position? But generally, the cut, it's not poorly done. It is actually quite well done. I'm not really disappointed about that. But now we need to, of course, as I said, we have not yet been told on when we are breaking for the elections. So we are having our cut on, thank you, Frida, at 10. Yeah, that's okay. 10 a.m. on Friday. So again, I'll come myself. I want to give the cut myself. So can we sign in? So again, I know fortunately you have done the anti-cancers, as I was telling you. I believe you even know more than me. I'm doing them after many, many years. I have to read quite a lot. The last time I did them was when I was in college. That's many years ago. So many things have changed. So again, remember, as we are mainly interested more on the chemistry aspect. Not, of course, the pharmacologists are there, and definitely I know they have questioned you on those areas where possible, and where the structure is not very complicated. It's usually good to give the structure. And even if we didn't do the proper number, at least you can indicate which carbon. We are talking about a substituent at a particular position. It is good to indicate which position you are talking about. So I think that, let us sign in, please. Sign in, please. And I think, God willing, tomorrow we are supposed to have a class tomorrow. Frida, you will confirm. And if we have one tomorrow, I think we can continue on the